Hi guys, sound check.
Yes, the sound works.
Was the lecture so awful that no one came here except you?
Well, I hope that's not the case.
Well, no problem. If you're the only one who will discuss everything personally, that's not an issue for me. The issue, well, actually, even if no one comes, it's not an issue. It's even an advantage. You just do nothing. But this case is also not an issue. Yeah, probably there is some problem with finding the correct link.
Well, possibly.
Okay, people are coming, at least. Okay, yeah, now it's fine. People are coming. So let's wait like for 1 minute at least, and we will start in 1 minute or probably in 2 minutes. Okay, there are like 10 of us, including me and the manager. Okay. Yeah, I was afraid for a second that you're not going to come here. You're not willing to take part in the seminar. Okay, people are still coming. So, well, I will keep talking. What are we going to do today? So our goal is to understand the finite fields. So we just want to compute them, compute some elements there in here, and discuss some properties, how to solve different problems regarding finite fields, and discuss the Galois random generator, etc. And probably we will apply the random generator to the Stern ciphers. Okay, but let's start with a simple question. Well, here is a list of integer numbers from 1 to 10. Find all possible numbers here such that there exists a field with n elements. Could you write all the options? Oh, yeah. 2, 2, 3. Let me repeat. There is an answer in the chat. So 2, 3, 4, 5, 7, 8, 9. So we excluded 1, we excluded 6, and we excluded 10. Okay, yeah, that's the right answer. So there are fields with 2, 3, 4, 5, 7, 8, and 9 elements. And there is no field with 1, 6, or 10 elements. So let me clarify the reason why there is no field with 1 element. By the way, who knows the answer? Why there is no field with 1 element?
Because 1 should not be equal to 0?
Yep, exactly. 1 must be not equal to 0. If there is only 1 element, and you must have 0 and 1, they are the same. So this is because 1 is not equal to 0 in F. Exactly, this is the reason. So now, why 6 is impossible? By the way, Anton, yeah, you can explain this like 1 is not prime, but there are some subtleties, like 1 is an invertible element, and when we discuss primes, we just discuss non-invertible ones, so you have to deal with invertible elements in a separate manner. So usually it's just better to find a different argument for an invertible element.
Got it.
Again, so why 6 is impossible? Who knows? Except for Anton, who gave the answer. Okay, who needs an explanation? Okay, write into the chat who needs an explanation why the blue numbers are possible and red numbers are impossible. Okay. So let me recall. So the main claim was, if you have a finite field, then it must have p to the n elements, where p is prime and n is any positive integer. And actually, any power is possible. So for any p and positive integer n, for any prime p and positive integer n, there exists a unique field F containing p to the n element. So how do you find all options here? You just can find for the elements which are powers of a prime number. So here, 2 is the first power of prime number. 3 is the first power of prime number. 4 is the second power of prime number. 5 is the first power of prime number. 7 is the first power of prime number. 8 is the third power of a prime number. And 9 is the second power of a prime number. So all these options are valid for our case. So all of them are of the form p to the n, where p is prime. But if you consider the red numbers, so I have already explained why 1 is not a valid option, but 6 is the product of 2 and 3. It's not a power of prime, and 10 is 2 times 5. It's not a power of prime. So that's why there is no field with 6 or 10 elements. Now, are there any questions so far? Okay, so yeah, that's a simple question, and that's a good candidate for the first question during the exam, actually. So it's good to know the answer here. So it's a way to check if you understand what's going on or not. Now I would like to discuss one technical tool, which is called Frobenius automorphism. we didn't have enough time to discuss it during the lecture, but it helps to compute when you deal with finite fields. Well, suppose we're given a field, F is a field, not necessarily finite, but we want its characteristic to be prime. So it's a prime non-zero number. Then we may consider a map from F to F, taking x to the p, where p is exactly the characteristic. Then the claim is this map is a homomorphism of rings. It's a, well, actually, automorphism is probably a bad choice here. Let me say endomorphism. I'm sorry for doing that, but since I have chosen a more general case, I have to say endomorphism. So, well, my claim that phi is a homomorphism. So this means that it preserves addition, multiplication, and the identity element. So let's check. And later I will explain the term endomorphism, what it means, actually. So, well, it's quite easy to check that phi preserves the identity, well, just because identity to any power is the identity element. Also, it's clear that it preserves the product because, well, just a to the p, b to the p, because a field is commutative. So the interesting part is how to check that it preserves the addition. But in this case, we can compute, we can expand this expression, and we will get the sum. K goes from 0 to p, and here CPK, a to the k, b to the p minus k, or if you prefer a different notation, choose k of p elements, and the a to the k, b to the p minus k, the sum, where k goes from 0 to p. And let's look at this expression. Well, if you take k to be 0, it will be b to the p. If you take to be p, it will be a to be p. Let's now take any k strictly greater than 0 and smaller than p. Then its number, like this, and just by definition, it's computed as this. Okay? And the result is always integer. But now, you see here, we have p times p minus 1 factorial. So the prime number p appears here in the numerator. Now, let's take a look at the denominator. In the denominator, this is a product of elements from 1 to k. And because of this, k is strictly smaller than p, and there is no p here. So p does not appear here. On the other hand, if you look at this expression, it's a product of elements from 1 to p minus k, and since k is strictly greater than 0, then here also p doesn't appear. Okay, so the prime number p appears in the numerator, but it doesn't appear in the denominator. It means that the resulting integer is divisible by p. So p divides this number if k is strictly greater than 0 and strictly smaller than p. But if the characteristic is P, then Pk times anything is equal to 0 for any x in F. I mean, in the latter case, in this case, which means that in this sum, only the first and the last summand are non-zero, and the result is a to the p plus b to the p. Let me show you the whole computation. Are there any questions regarding that? So, in particular, this map gives you a homomorphism. And actually, a homomorphism of fields is always injective. So it's an injective homomorphism. I will explain in a minute why every homomorphism of fields is injective. But in general, this homomorphism need not be surjective. And the word endomorphism means a homomorphism from a field to itself or from a ring to itself. This means endomorphism. So let me explain why homomorphism of a field is injective. But okay, so if we have a homomorphism from any field, actually to any ring R, then, well, if it's not, so in order to prove that it's injective, we need to show that the kernel is 0. But kernel of our homomorphism is an ideal of a field F. And let me suppose that the kernel is not 0. So suppose a contrary holds that the kernel is not 0, then it means that the kernel contains some element. But then x minus 1 times x must be in the kernel, which means that the element 1 is in the kernel. This is just by definition of the ideal. The kernel is always an ideal. But if 1 is in the kernel, then for any element y from F, y times 1 must be in the kernel by the definition of the ideal, because the kernel is an ideal. But then it simply means that if the kernel is not 0, then the kernel must be the whole field. But in this case, if it simply means that 0 and 1 goes to the same element, 0. Well, yeah, and here I suppose that the ring R is not 0. So if the ring R is not 0, then 1 and 0 are two different elements, and this is impossible. So in particular, if you consider a homomorphism from a field to another field, then it's always injective. Are there any questions regarding this? Should I repeat something? Okay.
I don't quite understand the proof.
Oh, you don't understand the proof. Okay, so let me recall that if you have a homomorphism of rings, then it's injective if and only if the kernel is 0, okay?
Yeah, but I don't understand why if x belongs to a kernel, then x times x inverse
okay.
belongs.
Let me show this explicitly. But so how to check? So here I use the fact that the kernel is an ideal. So this is an ideal. The kernel is always an ideal. But by the definition of an ideal, if something belongs to the ideal, you can multiply it by any element of your ring, and the result must be inside the ideal. Okay?
Okay.
But if you want to check this directly, we can do that. Let me show you. It's not hard. You just how to check that this product is in the kernel. In order to check that something is in the kernel, you just need to show that this something goes to 0. So let's just compute the image of this product. Since phi is a homomorphism, is equal to this product, But now we know that x is in the kernel, then the second factor is 0, so the result is also 0. So this computation shows that this product is in the kernel indeed. Okay?
Okay.
Mm-hmm. Are there any other questions? Okay, so now I want to switch to the case of finite fields. So if we have a finite field, say fp to the n, its characteristic is p. Its characteristic is p. Then we have this Frobenius homomorphism. And we know that it's a homomorphism and it's injective because every homomorphism of fields is injective. It's injective homomorphism, as we already seen. But since this set is finite and phi is an injective map, it must be surjective automatically. So the surjectivity is immediate here. So in this case, phi is an isomorphism. So for finite fields, the Frobenius homomorphism is an isomorphism. So this is Frobenius, and we say it's automorphism. Automorphism means that it's an isomorphism from a field to exactly the same field. So the word auto means that the target and the source for the map are the same. So in particular, this means that in a finite field, if you want to compute something like a plus b to the power of p, you just write immediately that it's a plus b, or a times a to the power of p plus b to the power of p. Or if you want to compute a plus b to the power of p plus 1, you just rewrite it as this. And then for the first factor, you use the fact that the Frobenius automorphism preserves the sum, and then you just need to multiply these two brackets. So you see, instead of writing to the p plus 1 power and expand all the products, you just simplify it by directly applying the Frobenius automorphism here. This is one of the ways how to use the Frobenius automorphism. Another application of the Frobenius automorphism is this. In a finite field, if you have an element B of a finite field, A of the finite field, you can always solve for X this equation. So there is always a unique X solving this equation. Well, because the Frobenius automorphism is surjective. Well, it's actually bijective. So there is only one X giving you A after rising to the power of P. So these are the remarks regarding the Frobenius automorphism. Are there any questions regarding this? So I will use these tricks to compute powers in finite fields. So let's go and compute something with finite fields. Okay. So the simple example at the beginning. So let's take Z2. How do we produce a field of 4 elements? So I want to produce a field with 4 elements. Let me recall. So first of all, 4 is just a power of 2. So here we'll look at the power, and we need to find a polynomial, an irreducible polynomial f in Z2 of x, irreducible, such that the degree of f is equal to 2, where 2 is the power. So this is this 2. So here it's easy to make a mistake, which element is supposed to be here, but I mean, the degree is the power of the prime number, not the prime number itself. Okay, and we already know how to compute all irreducible polynomials over Z2 for second and the third degree, and there is only one irreducible polynomial of degree 2, and this irreducible polynomial is this one. For the power of, for the second degree, the polynomial is irreducible if and only if it has no roots. And there are only two options for the root, 0 or 1, and neither of them is the root of this polynomial. And the same thing happens for the polynomials of degree 3. A polynomial of degree 3 is irreducible if and only if it doesn't have a root. But now let's discuss the polynomials of degree 2. So now the the field F4 is produced as the quotient Z2x, quotient by x squared plus x plus 1, and explicitly it consists of all polynomials of degree strictly smaller than 2, and the coefficients are here. So this is our field. Now, let's compute the product of two elements, a plus b times x times c plus d times x. Could you tell me the result? So it should be presented in the form something plus something times x. By the way, is there anyone who doesn't know how to compute this? Please write into the chat. I just want to be sure that everyone knows what to do. Okay. Okay, should I wait for the answer or should I explain the answer?
Explain
Should it be
please.
something like AC plus BC? No, not here, but
Okay.
I mean AC is here, but near X is going to be
here.
BD.
Let me write the answer. It will be so, and I will compute the answer. AD plus BC plus BD. This is how it looks like. So let me compute this. So you just open the brackets. So it's AC plus ADX plus CBX plus BDX squared. Now, this part is already in the required form. We just need to factor out the x. But in order to compute this, we need to replace x squared by its remainder modular x squared plus x plus 1. But x squared equals 1 plus x modular x squared plus x plus 1. So in this ring, F4 in this field, this guy is equal to this guy. So we just proceed with this plus BD 1 plus x. And now we just combine this term with this term and the second part with this term. So as you can see, we have AC plus BD here and AD plus CB plus BD here. So this is how to compute the product for any two elements of this field. Are there any questions? So as I prefer to think about this computation, so when you compute something like this, so you see we we define our field as z2x quotient by this expression. And this simply means that this expression is 0 in this field. So in our field F4, we have x squared plus x plus 1 equals 0 in F4, just by definition, because the left-hand side must be considered modular x squared plus x plus 1, but it's exactly x squared plus x plus 1, so it must be 0 in F4. But now we can move this part on the right to the right-hand side, so x squared equals x plus 1. So, and now we use this expression in order to simplify all the powers of x. Okay, now what can we say about a F4 star? It's a cyclic group. So it must be isomorphic to a cyclic group, but which one exactly? So F4 has 4 elements. F4 star has 1 element less because we exclude the 0 element. So it must be a cyclic group of 3 elements, so it's Z3. Okay. What are elements of Z3? They are non-zero elements of F4. So precisely this is 1, x, 1 plus x. So what are the generators of this group?
One plus x.
Actually, x and 1 plus x, there are 2 generators. And why is that? Well, here it's a cyclic group of prime order. So if you have a group of prime order, then for every non-identity element is a generator. This is just a reminder. So if you remember, we discussed this as one of the corollaries of the Lagrange theorem. If you have a group of prime order and you take an arbitrary non-identity element, then it's a generator. So in this case, it's very easy to get a generator, any non-identity element. So F4 star here is generated by x, and it's also generated by 1 plus x. And you see, if you take x, let's compute explicitly the powers of the element x. So x to the 0 is 1, x to the 1 is x, and x squared, we'll know by this expression, x squared is x plus 1. So yes, all of these elements are the powers of x. We can do exactly the same computation in case of 1 plus x. Well, again, 1 plus x to the 0 is just 1. 1 plus x to the 1 is just 1 plus x. And when we compute 1 plus x squared, well, it's exactly, since we're in the characteristic 2, it's 1 squared plus x squared. But x squared is 1 plus x. And the result is x, because 1 plus 1 is 2. So I mean, you can do it without computation. It's clear that if you have a generator x, then its second power must be the second non-identity element. But I just wanted to demonstrate the computation here for 1 plus x, for the element 1 plus x. Okay, but this is a simple example. Let's consider a different one. So suppose we want to produce the field F8. So for that, we should find an irreducible polynomial of degree 3. Why? Because 8 is the third power of 2. So we need an irreducible polynomial of degree 3. Well, so if we write down all options for a polynomial of degree 3, these are all possible polynomials of degree 3, and it's irreducible if and only if it has no roots. So what are the options for the roots? 0 or 1? Well, 0 is the root of this polynomial if and only if c is 0. So if we want to exclude 0 from the set of roots, we should consider polynomials of this form. Then 0 is not a root. Now, when the element 1 is a root, well, the element 1 is a root if and only if there are even number of terms in this expression. So there are only two irreducible polynomials of degree 3, x cubed plus x squared plus 1, or x cubed plus x plus 1. Just in case, are there any questions regarding how I found all the irreducible polynomials of degree 3? Okay, so now we can produce our field using either of these polynomials. So I can produce f8 as z2x modular x cubed plus x squared plus 1, or I can produce it in a different, using the different polynomial, the other one. I will use a different letter because I want to distinguish the elements of the fields. So it changed nothing but just the name of the variable. So this will be the second model for our field f8. So what are the elements here? The elements here are the polynomials of degree at most 2, and the coefficients are e in z2. What are the elements here? The elements here are exactly the same expressions, and the coefficients are in z2. Oh, I'm sorry, there must be y instead of x on the right-hand side, I'm sorry. Let me replace it. So you see, these two sets are exactly the same. So what's the difference?
Well, I guess multiplication would work a bit kind of different. Well, there should be isomorphic, but if we don't consider them as isomorphic, the multiplication should be a little bit different, maybe, because we have different.
You're right. Exactly. The only difference between the left-hand side and the right-hand side is the multiplication, because even addition is exactly the same. So when you add these expressions together, you just add them coefficient-wise, and exactly the same it works here. If you add two expressions like this, you add them coefficient-wise. The difference will be multiplication. So, for example, if you want to multiply x times x squared here, you will get x cubed, and the result is 1 plus x squared, because you must take the result modular this polynomial. So this is the place when it appears, because you take it modular x squared plus x cubed plus x squared plus 1. But if you multiply y times y squared here, you will get again y cubed, but now you have to take the remainder modular different polynomial. So the remainder will be 1 plus y modular y cubed plus y plus 1. So this is the difference between these two fields. Well, they're isomorphic, and we will find an isomorphism here, but first of all, we have to understand what's the difference. So you cannot just take x to y, because this map is not an isomorphism. And this is an example why it's not an isomorphism, because if you take x to y, then, so what you would do, so if you take x to y, simply, this is not an isomorphism, not a homomorphism.
Can I ask, just to clarify, x
Yep.
cubed is equal to minus x squared, but because we have z2, these are the same as just ones.
Yes, exactly. In Z2, -1 and 1 are the same elements. Yes, you're right. Exactly. So, so why this map is not a homomorphism? Well, it's actually written here. So if you first compute the product of elements x and x squared, you will get 1 plus x squared. And so if you consider this, you will get this. And if you take x to y, the result will be this one. But if you want it to be a homomorphism, you want it to be exactly the same thing as this product. But then it will be this product. And here, if we compute this thing, we should use this expression. But here it's 1 plus y, and these are different. So it doesn't work like that. So you cannot just substitute x by y. So what? How do we produce a homomorphism from between these rings? Okay, let me show you. So I just want to rewrite them. So we have x squared plus x cubed, sorry, plus x squared here, and here we have x cubed plus x plus 1. So we want to produce a homomorphism from left to right. But now, how do we find a homomorphism from this guy to this guy? Here, we use the general theorem. So, I have a piece of whiteboard here. So let me recall, there is a way to produce all homomorphisms from a ring like that to any possible ring R containing the field K. So if a ring R contains a field K, how do we produce a homomorphism from the left-hand side to the right-hand side? Well, we should find an element R here such that f of R is equal to 0. Then a homomorphism defined by this element R works like this. You take the polynomial g of x, which is an element of the left-hand side, and we substitute f by the element R. So we will get g of R. And this will always give you a well-defined homomorphism from this quotient ring to any other ring. This was discussed during the previous seminar, but just in case, I just want to recall the fact. So now, if, I wrote x also here, let me replace it by y, because I just want to have different letters, because when I start writing expressions, it will be hard to distinguish what I'm doing. So what I want to do here, I just want to find an element R here such that R cubed plus R squared plus 1 equals 0. Then my map, my homomorphism will work like this. I just substitute x by this element R. So I will write A plus BR plus CR squared. And this will be a homomorphism defined by the element R. Now, so this is just according to the rule I have described here. This is precisely what I need to do. Now, if it's a homomorphism, well, it must be injective, as we know, because the left-hand side is a field. But since the left-hand side and the right-hand side have exactly the same amount of elements, this injection is actually a surjection, so this is an isomorphism. So this is how to find an isomorphism between these two fields. Are there any questions regarding this? Okay, there's probably a question how to find such an element R? Well, somehow you have to solve this equation in this field. There are several options, and the best option is just try random elements, try to guess an answer, and probably if your guess is good enough, you will guess on the first or on the second step. So I believe that here you may guess. So let me show you, first of all, let me show you the general way how to solve this equation. So now we want to solve the equation r cubed plus r squared plus 1, but where? In z2y by y squared plus y plus 1. So y is not a solution of this equation because y is the solution of the, oops, here is y cubed. Because y is the solution of this equation, y cubed plus y plus 1 equals 0. And we have to solve for this equal to 0, is equal to 0. Well, in general, an arbitrary element of this field is of the form, I forgot the coefficient. So we just substitute this expression here instead of R, and we just find elements A, B, and C satisfying the resulting equations. So, I mean, let me show you how it works in general. It's unpleasant, but it works. So you write it like this. And then you compute the left-hand side, and the left-hand side will be in a form something plus something y plus something y squared, and it must be equal to 0. And by definition, this element is equal to 0 if and only if each coefficient is equal to 0. And then you will have a system containing 3 equations on the elements, and the elements A, B, and C are here. And you just solve this.
Will we have it in our homework?
What again?
Will we have such problem in our homework?
Yeah.
That's no.
But I'll try to make the problem as gentle as it's possible. I mean, I don't want you to die because of the computation. But still, I want you to do this by hands in some specific cases where the computation is simple. So, but instead of solving these equation directly, let me try to guess. And usually, what is the best candidate for a guess here? Let's try element y plus 1 instead of y. And let's check if it's a solution for this equation. So y plus 1 cubed plus y plus 1 squared plus 1. Let's just compute this. So you can do just by the brute force. Here you have only 8 elements. Just choose any coefficients here. Like, well, all the 0 elements are. Actually, you have only 7 options, because if you have only 0 coefficients, then you will never solve this equation. And also, at least B or C must be not 0, because if there is no y in this expression, the element A must be a solution of this equation. But this equation has no solutions in Z2. So, well, actually, there are 6 options, and you just substitute 6 different polynomials inside this expression and check which one is the solution. But so here I just want to try this one. So it's a good candidate for a solution. Well, here I can compute this expression as y squared plus 1, because we're in the characteristic 2. And here I will rewrite it as y squared plus 1 times y plus 1, because rising to the second power is an automorphism. So the result will be this. So let me expand this expression. It will be y cubed plus y squared plus y plus 1. The second bracket is y squared plus 1, and the last thing is plus 1 again. But now we know that y is the solution of this polynomial. Y cubed plus y plus 1 is 0, so I can cancel this, but y squared plus y squared also cancel each other, and 1 plus 1 also cancel each other. So the result is 0. So yes, y plus 1 is a good candidate. What's the good candidate for this equation? So we have 0 here. So now we can produce this homomorphism as this. We just take R to be 1 plus 1. And here the homomorphism works as this. It takes this expression a plus bx plus cx squared to the expression a plus b times 1 plus y plus c times 1 plus y squared. And then you can expand this expression and you will get the resulting polynomial. So this is one option for your isomorphism. There could be other solutions, but we need to find at least one isomorphism. Okay, and what about the map in the other direction? But just in case, is it clear so far how I found this isomorphism? Are there any questions regarding the process in general? Okay, but now what if I want to produce the inverse map? How do I produce the inverse map? I have to map y to some element. Well, you see here, we take x to the element 1 plus y. Then it simply means that x is equal to 1 plus y. This is how you should think of it. Then y must be equal, well, x plus 1 also. So if you, well, it must be x minus 1, but since plus 1 and minus 1 is the same thing, so exactly the same rule takes your y to the element x plus 1 on the left-hand side. So exactly the same rule gives you a homomorphism from the right-hand side to the left-hand side. And this homomorphism is automatically an isomorphism. So are there any questions regarding the last remark? How do we produce a map in the opposite direction? Okay. Yeah, now let's find the generator of the multiplicative group of this field using this and this representation. So suppose I want, let me go back here. I will repeat all the equations. Okay, it's okay. Now we have the first option is z2x quotient by x cubed plus x squared plus 1. And the second option was f8 equals z2x by z2y by y cubed plus y plus 1. Now, what is f8 star? It's an abelian group. What should I write on the right-hand side? Okay.
Something z
Yep.
6?
No, Z7.
Oh, 7.
Why? Because
Because it is cyclic, and we know that all elements of fields are invertible except 0.
yep, it's because F8 contains 8 elements, and F8 star contains 1 element less, so it contains 7 elements. And this group must be cyclic with 7 elements, so it's F star, F8 star is Z7. So it's in general, if you have Fp to the n star is isomorphic Zp to the n minus 1. This always holds. I mean, this is true in general for any prime number p and any natural number n. Okay, but now you see this group has prime order. It consists of 7 elements. So every non-identity element is a generator. So in particular, both elements x and y are generators in this case. So if we use the left representation, then F8 star is generated by the powers of x. And if we use the right representation, then F8 star is generated by y. Well, in particular, this means that x can be expressed as a power of y, and y can be expressed as a power of x. But this expression actually shows that y cubed is 1 plus y, and as we know, our isomorphism, this element corresponds to x, actually. Well, so so this is one of the ways to find well, a solution for your equation. So this shows you that when you want to find a solution for this equation here, then you, instead of taking elements in the form a plus by plus cy squared, you can take them in the form y to the power of d, because y was a generator for this group. So every non-zero element of this group is representable in this form, so you can find a solution in this form. But why is it better? Because, well, when you use just powers of d, the only knowledge you need to use is this one, that the third power of y is just 1 plus y, and it's simpler to deal with this expression consisting of one unknown letter. So how would I solve for r? Well, my first attempt is to take r to be y. Well, we know that y is not a solution of this polynomial, because, well, y is the solution of the other one, where the power here is 1 instead of 2. So that's a bad option. The second try is r to the power of r is equal to the second power of y. So how would we compute this? Y square cube plus y square square plus 1. Then it's equal y cubed, let's say, square plus y fourth plus 1. Now I use y cubed is equal to 1 plus y squared plus y fourth plus 1. And then I compute it like 1 plus y squared plus, and y fourth is equal to y times y cubed, and it's equal y times 1 plus y and plus 1 here. And if we expand it even further, so we cancel 1 and 1, then we cancel this and y squared, and the result will be just y, which is not 0. So this is a bad option. And now, so just in case, is it clear how I computed the result? Should I repeat this? Should I go slower? Okay, and then you can do this with the third power. So you do it like this. And then, well, you use this. And then the computation is exactly the same as we did, and the result is 0. So on the second step, we'll find the required element. So instead of using the coefficient-wise representation, you can use the power, the representation of each element of this field as the power of the element y. So if the polynomial is chosen in such a way that y is a generator of the multiplicative group, then it's easy to find a root of any equation. You just find the root of equation in this form as the power of the element y. So this is the main trick, how to simplify the work here. And actually, you should never consider the first option, the first power. It should never be considered, so you just don't waste time. And you see here the second attempt is successful. Okay, now let's discuss the random generator based on this field F8. Okay. So again, we have two options for our field. The first one, F8 is equal to Z2X quotient by X cubed plus X squared plus 1. And the second option is F8 is equal to Z2X quotient by X. I'm sorry, I always do the same thing. I forget to switch the name of the variable. Okay, so let me recall the way you produce a random generator using a finite field. So you can, first of all, you should take some representation for your finite fields. Let's say we take this one. The second step, we consider the multiplicative group, and we must choose a generator. So here G must be a generator, and in our case, we're lucky, we can take the generator to be X. You can choose any other generator, but if this X is already a generator, it will be simpler to use, and you will see why. So let's stick to this one. And then we should take an arbitrary element H from F8 such that H is not 0. Well, for example, I could take H to be something like 1 plus X squared. Why not? Then I produce, so now I want to produce a sequence of random sequences. So what generator does, it actually gives you a sequence. When you ask it's the second time, it gives you a sequence, etc., etc. Now, what kind of sequences are we getting here? We want to get a sequence of length 3 consisting of 0 and 1s. So, but before going to sequences, let's deal with the elements of the generator. So I want to produce this sequence of elements. So when someone asks me the first time, give me an element of F8, I'll give him H. The second time someone asks me, give me an element of F8, I'll give him H times G. The third time someone asks me, I'll give him H times G squared, etc. But now I have to translate the names of the elements into the language of sequences. So the element H is equal to 1 plus 0x plus 1 x squared. So it corresponds to a sequence 1, 0, 1. Now I want to compute h times g, which is 1 plus x squared times x. The result is x plus x cubed, and x cubed is equal to 1 plus x squared. So it will be 1 plus x squared. And this thing corresponds to the sequence 1, 1, 1. The third time someone asks me, I'll give him this result. So this will be 1 plus x squared times x squared. Well, this is the same as multiply the previous result by x. So it will be 1 plus x squared times x. The result will be x plus x squared plus x cubed. And x cubed is equal to 1 plus x squared. So x squared and x squared cancel each other. So the result will be 1 plus x. And 1 plus x corresponds to the sequence 1, 1, 0. And I can proceed in a similar way and compute all the sequences. So my random generator generates a sequence of the length 3 consisting of 0 and 1s. So here 8 was a third power of 2. So the length of the sequence, is equal to the power. And this 2 corresponds to the number of elements in the sequence. Oh, I mean, the number of options for each coordinate in the sequence. So since here we have 2, so there are only 2 options for each coordinate, either 1 or 0. If we had 3 here, then there were 2 options for each coordinate, 0, 1, and 2, or 0, 1, and minus 1. It depends on how we wish to represent elements of Z3. So when I ask my generator the first time, it gives me this sequence. When I ask the second time, it gives me this sequence, and so on. Now, is it clear how it works? Are there any questions regarding this procedure? Okay, now I want to discuss how to do this in a matrix form. There is a simpler way to compute this, because you see you have to deal with polynomials, multiply them, then cancel some elements, but you can do this using just matrices. And let me show how to do this in a matrix form. So matrix approach, one column. So I will stick to the same representation of F8. So it will be Z2x quotient by x cubed plus x squared plus 1. Now, if we consider a map phi from F8 to F8, which is multiplication by x, so any element g goes to x times g, then this is a linear map over Z2. So F8 is a vector space over Z2 of dimension 3. And this is a linear map. This is Z2 linear map. So we can, but we know that if we have a vector space, a finite dimensional vector space, we can replace it by the space of sequences, and every linear map between spaces of sequences is given by a matrix. So let me take elements 1, x, and x squared as a basis of F8. Then I can identify F8 with Z2 square or cube in the following way. A vector ABC corresponds to the linear combination A plus BX plus CX squared. So this is how I replace F8 by Z2 cubed. But now I want to compute my map phi after this replacement. So if I replace F8 by Z2 cubed, I should get a map taking A, B, C to something. And the map is just multiplication by X. So how do I compute this? So I need to compute the matrix of this linear operator using this basis. So this simply means I have to find a matrix which suits for this equality. There must be a 3 by 3 matrix. So what should I do? I should apply, so, and my map phi of G is equal to X times G. Is it clear what's written here?
Yes.
And why do we have to map vector AB with coordinates ABC to somewhere?
Because you see, I have this map phi from F8 to F8, which takes G to X times G. I want to replace F8 by Z2 cubed, F8 by Z2 cubed, but then our polynomial G becomes a vector. So I just want to know how to compute this map in terms of vectors. I just want to find the image of this vector. And it must be some multiplication by a matrix A, 3 by 3 matrix. So it must go to something like this. And the purpose is to find this matrix A. Then this will be exactly this map. And if you see how our random generator works, it starts from a vector ABC, which is given by H. So here ABC will be 1, 0, 1. And the next element will be this element times matrix A on the left. So if you know this matrix, your random generator works as follows. You start with some vector, and then you just multiply by the matrix A on the left, and the next result will be computed by applying the matrix A to the previous result of your random generator. Okay?
Okay.
And here, if you compute the matrix of this linear operator using this basis, the result will be this. So 1, after applying phi, goes to X. So it has coefficients 0, 1, 0, because 1 goes to X. Then X goes to X squared. So the coefficients are 0, 0, 1. And the element X squared goes to X cubed, and X cubed is 1 plus X squared. So the coefficients are 1, 0, 1. So this coefficient goes here. The 0 coefficient is here. And this coefficient near X squared goes here. Because when you multiply this by this, like 1 times 1, X times 0, X squared times 1, you will get the image of X2, X squared. So this is your matrix A. So now, if you take H to be 1, 0, 1, then how do you compute the next element? You just multiply by the matrix A. So if you multiply by the matrix, you'll see you will get 1, 1, 1. Now, just apply matrix again. So you will get 1, 1, 0. Apply it again. You see, it's much quicker to compute using matrix multiplication. Here you will get 0, 1, 1. Then if you apply it again, I just don't want to forget the matrix. You will get 1, 0, 1, and this is the element H again. So this is exactly the same element H. So now you're just working in a cycle. So this guy goes. No, I'm sorry. There was a mistake somewhere. It shouldn't be. Oh no. I'm sorry. This goes to this one, 1, 0, 0, and if you apply it again, it goes to 0, 1, 0, and if you apply it again, it goes to 0, 0, 1, and if you apply it again, then it goes to H. I'm sorry. You must cycle through all non-zero sequences of the length 3. And as you can see, here we cycle through all the elements. So this is a random generator based on a finite field. Okay, are there any questions regarding this procedure? I hope it was clear, at least. Okay. By the way, we have like 3 minutes, and I want to discuss one additional question. It will be useful. So, for example, if I want to find, well, if I want to produce this field F16, it will be Z2X quotient by, and I can take this polynomial X4, X3 plus 1. Then, well, its multiplicative group will be Z15, 16 minus 1. Well, and 15 is not a prime number, so it's just a product of Z5 and Z3. So how do we find a generator here? I mean, I just want to discuss a way to find a generator. So, well, how to check that X is a generator? Well, whether or not is it a generator? I mean, how to check this? Is it true that X is a generator here? Well, if 15 were a prime number, it would be simple. X is not an identity element, then it's a generator. But how do you check it here? So here is the problem. So if you take an abelian group of order n, so here n is equal to 15. Well, you can express the order as the product of prime numbers. Then there is a receipt how to check if an element is a generator. So suppose you're given an element G of the group G. How to check if it's a generator or not? Here is the algorithm. You just define, for each prime divisor of n, you define the number qi, which is n divided by pi. So there are different distinct prime divisors of n, and there will be r numbers qi. So I goes from 1 to r. And then you compute g to qi. And it must be not equal to 1 for each I. So G is a generator if and only if this holds. I just don't want to prove it. Well, simply I don't have time for doing that. But this is how you check an element for being a generator. So in our case, let me apply it in our case. So in our case, we know that, so our group G is F16 star. The order of G is 15. There are 2 prime numbers, 3 and 5. So Q is 15 divided by 3 is 5, Q1. Q2 is 15 divided by 5 is 3. So now, in order to check if something is a generator of this group. For example, if we want to check if X is a generator, we have to compute X to the 5, X to the 3, and compare the result with the identity element. So if in both cases the result is not equal to 1, then X is a generator. If at least in one case the result is 1, then X is not a generator. So in this case, we see that X cubed, well, is not equal to 1 because, well, the elements here are polynomials of this form. Oops, let me move the blackboard. So they are uniquely expressed in this form. So X cubed is not equal to 1 because, like modular this polynomial, they're distant. So this is checked. So now we have to compute X to the 5, and this is equal to X times X to the 4, and this is, and X to the 4 is just 1 plus X cubed, and the result here is X plus X to the 4, and again, X to the 4 is 1 plus X cubed, so the result is 1 plus X cubed, and this is not equal to 1. And here we know that the element X is a generator of the multiplicative group of the field F16. So this is how you check in general that an element is a generator. And if you're not lucky and X is not a generator, so the next choice you could do is to consider X plus 1 or something. Just try to find a generator in a simple form, as simple as possible. Okay, well, I have -2 minutes, so if you have any questions, please ask. If not, then thank you for being here. Okay, there are no questions, I guess. Okay, guys, thank you.
Thank you.
Bye.